Hello and welcome back to another episode of the Oxford Online Maths Club. My name's James and today I'm joined by Miles.
Hello, I'm Miles. I do stuff on the Oxford Online Maths Club now. It's interesting.
Miles is here to talk about projective geometry, which is the episode we're going. And Miles has put an axiom on the board before we've even gone live.
Yeah.
Do you want to read that out?
So this is a proposition, and I'm proposing that any two distinct lines on a plane intersect at exactly 1 point.
Any two distinct lines. You put distinct lines
So here's
in
some
there.
distinct lines.
Yeah, okay.
Well, if they're not distinct, then we sort of have an issue where there's two lines on top of each other and they have lots of intersections because they are the same line. So
Right.
I'm going to make sure that they are distinct.
Two distinct.
And they intersect at exactly 1 point, which is brilliant.
Bro, right, okay, you play with that. I'll talk to chat, say hi to people I can see. I can see Herb in chat and Zoe in chat, an anonymous person, and Arya, and I think I saw Shrist a moment ago. Herb is supposed to be writing 5,000 words on 3D geometry, so maybe this counts. Are we doing anything 3D? We might see some 3D
Oh, a
stuff.
little bit.
We might see some 3D stuff. As always, we've got a poll at the start. I like to know how people's day is going. You can vote in this poll over at slido.com/ I can't remember what the end of the URL is. It is on screen. Slido.com/OOMC. I forgot the name of my own show. People are voting for 4 and 5 and 3 stars so far. If you'd like to join in, it's down there. You can be anonymous. No one has to tell me who they are. Hello to, exactly as I said that, hello to an anonymous person over there. Right, Miles is happily drawing pairs of distinct lines on a plane, and so far they've all intersected at exactly 1 point. Never 2 points, never 0 points, never 100 points. Always exactly 1 point. Interesting. Okay, let us know in chat what you think about that claim. We're seeing a lot of examples, but
Yeah, I
people
can't
in
think
chat
of any
might
lines
have
that don't intersect at 1 point.
People are doing some retakes. B is here as well. Hi to B. YouTube's giving me a warning message, which it normally does when my computer heats up too much.
Parallel lines.
Oh.
Parallel
Okay, so we
lines
got
are
a challenge.
definitely the same line. They're not the same line,
Not
sorry.
the same line, right?
Depends. Are they on top of each other? No, then they're not the same line. So, let's see. Maybe
Yeah,
I'll
do you
put
want to
one
draw some parallel
here.
lines?
What point do these intersect? That's a hard question because it seems like there aren't any. I mean, we know that about parallel. That's a classic thing that we know about parallel lines is that they don't intersect at any points whatsoever. So if I look, along this parallel line forever and ever and ever, and I keep going, they would never touch, right? We know this. Well, there are some ways, or some sort of, I don't know. There's some model or visualization where they do. So here I have. Would you agree with me that these are two parallel lines? I think they're pretty parallel. James,
I'm trying to see they're crossing some points. So you're looking straight down at the origin. And I should say, this is you're doing this live, right? You're in.
I'm moving around right now.
You've built a
I'm
kind of
jumping up and
3D
down.
environment for us with parallel lines in. So
And
that
here
we
are the
can
lines
examine.
that were on the board. I've just popped
Oh,
them
I see.
down here.
Okay. So they're going through some grid points. They look like they've got gradient.
Yeah.
Both got gradient 1.
They do
And
both
that might
have gradient
be
1.
y equals x plus 1 and y equals x minus 1. Can you look
That is the case.
right a little bit for me
So-
to check that they keep going through the points?
Yeah.
They keep going through grid points over there.
Oh,
Yeah, they look pretty parallel to me. Okay.
they are definitely parallel, but
And
is it
then-
me? Or do they look like they're intersecting?
Right. Do they look
I
like
am
they're
Mark Jack,
intersecting?
who was in the Matt live stream in the chat last year.
Yeah.
Yes. These, as far as I'm concerned, are intersecting. Someone made a very interesting point that they intersect in spheres. Okay, we're going to come back to that, maybe in half an hour.
Mm. So
Someone already
today,
knows
I guess
what we're
today
doing.
we're looking at other sorts of geometry.
Denver. That's a spoiler.
So in projective geometry, it's a different sort of geometry to the sort that you learn in school. Where in school you have parallel lines in the plane and they don't intersect at any points. Projective geometry is a different interpretation which insists that every pair of lines do intersect at exactly 1 point. That thing that Miles I think quite cheekily put on the board that this is not true for the geometry you learn at GCSE or equivalent. But projective geometry is an example of a geometry where this is true.
A lot of people are mentioning that parallel lines intersect on non-Euclidean geometries, on longitudinal. So that's talking about spheres again.
I'm pleased.
Talking about lines plotted on a plane right now.
I'm really pleased by how much chat is suggesting things about spherical geometry and in general non-Euclidean geometry. It seems like people have maybe seen other examples already. I particularly like these Aya's example of what's going on a sphere. I've got a sphere. You could have different kind of parallel lines going around the lines of longitude that meet at both poles.
So someone asked what software I'm in. This is actually Unreal Engine 5, and I've just taken the floor and I've made it really big and done some stuff there. But other than that, yeah, as some of you might actually recognise that this is the default scene in Unreal Engine 5. The boxes hanging around. Anyway, so we're interested in this because, as far as I'm concerned, in our usual geometry with just a plane, there is no intersection for these parallel lines, right? But there seems to be some certain geometry, which is the one that we experience when we see. The way that our vision works somehow seems to make these lines intersect at this point. Where is this point? That's a good question to ask. Where is it? So, yes, someone said if they are the same line, then they intersect at infinitely many points. I'm only talking about distinct lines, so they can't be the same one. And these lines here, they have a distance between them. And as I look further away, that distance seems to get shorter and shorter as I look further on. So one could imagine that as I kept going, as I kept walking, or not walking, but as I kept looking further and further along these lines, then when I got infinitely far away, the distance between them would be 0. Or they would be touching. As seen from, our vision, I suppose. It's a bit hard to say as seen from our seeing, but what if they get infinitely close but don't intersect? So we have an idea about a way that we could build something maybe that would work. Okay, we've got lots of questions coming in.
Yeah, I guess the
Is there some angle at which you can put lines such that they appear parallel from your viewpoint? That is a good question. We'll come back to it.
I guess the kind of almost artificial thing that projective geometry adds in is that point where they appear to meet on the horizon. It's not a real point in the plane because there's no such point in normal 2D Euclidean geometry where those lines meet. The kind of artificial addition for projective geometry is to add in a point at infinity for them to meet.
We're trying to make a geometry that describes or is somehow similar to the way that we see, because in the way that we see, it seems like this axiom or this postulate might be true, that they do intersect at a point. So if I want to make some kind of geometry where that postulate is true, then I should look to the way that I see as inspiration. Someone says, if you look in the other direction, wouldn't they intersect at another point? So let's actually look behind us. There is what seems to be another point, and then Zoe immediately, maybe they are the same point. So we're looking around, right? We're looking around in real life, or in real life, we're looking around in the game, and we can see stuff that looks like it might inspire us to make something mathematical in which this postulate is true. So let's go on a bit of let's go a bit crazy, and I have two lines, and here's their point of intersection, right? This looks to be, let's pretend it's this way up, it's x equals 1. So as I take these lines and I sort of tug them like this, you can see I'm sort of rotating them in this way on either side. The point of intersection is getting further out, right? Then if I start here and I go and I sort of push them, that point of intersection is getting further out, right? And if I push them until they were parallel, then that point of intersection, the same way that this one is sort of at this strange point infinitely far away, we have the same situation here again. They're at this point infinitely far away. And now, if I continue the exact same movement I was doing before, so I'm sort of tugging on them, so that they rotate around and this point of intersection gets further away, something quite interesting happens.
Can you do it again slightly slower?
Yeah,
so
let's do it again slower. So
you're changing the gradient of the lines, so that the point of intersection is moving away, it vanishes off to infinity, and then you look behind you and keep going,
and it
comes back in again from over there. So I suppose
if I sent a train down there would be some problems eventually. Well, this train would have to go infinitely far for there to be any kind of problem. So I think, given infinite time, we might have an issue. But as far as I'm concerned, there's no problem.
I think what this experiment demonstrates with the changing gradient, it illustrates how the concept of a point at infinity helps to kind of fill in a missing gap. Otherwise it would be a kind of weird special case that the point of intersection is there and there. Off it goes. Oh, special case if they're parallel.
Where is it? Oh, strange.
And then you
so
keep
it
going.
Seems natural. Yeah, there's one intersection, one intersection, one intersection, one intersection, one intersection, one intersection. 0 or 2, according to some people. One intersection, one intersection. I think it's probably natural to suggest that there is one intersection at infinity, and we're actually seeing the someone talking about the train service taking infinite time. This point and this point are the same point. Perhaps we're just making suppositions. Maybe there is a way in which we can make all these ideas work together into a mathematical model. So it seems interesting. It seems like something worth exploring. Let's just have a look at some, classic shapes.
Oh wait, can I look at the two intersecting lines again? I've had a thought about.
Oh yeah.
I'm interested in the nature of the horizon because, so I have just two normal intersecting lines. What we're investigating, I guess, is it possible to have any two pairs, any two lines meeting at one point, and what we see so far is maybe the point straight ahead of me is the same thing as the point straight behind me.
Directly behind me.
Because you've seen the intersection point kind of move through that point. And maybe my intuition now is that all of the horizon in every direction counts as one point and infinity. It feels a bit like maybe positive infinity and negative infinity are kind of the same thing. So maybe infinitely in every direction should be some point at infinity. But if that would be a problem. Let me show you why that's a problem. If you bring the line back in, Miles, so that we've got two just crossing lines, we can see the point of intersection.
That
looks like about 4 lines.
You want a different one?
Yeah, just like this, right?
Right.
So here's the problem. If the horizon counts as just 1 point, if that's the innovation to put in 1 point at infinity, hand wavy 1 point at infinity, then that gives you a point of intersection for parallel lines. But oh no, these lines, which already have a point of intersection, they both go shooting off to infinity.
Yeah.
And if that's all the same point, if that all counts as the point of infinity, then oh no, these garden normal lines have now got a second point of intersection. So I kind of want to see if chat can think about a way around that, a way to get out of that kind of conundrum. We would like it to be the case, to fill in the gaps, if every pair of lines had exactly one point of intersection. I think I'm doing that as a challenge for chat. Oh, here are a bunch of lines, right?
Popping in some more. So these two, unfortunately they're the same colour, but these two are parallel. And this is another set of two lines that are also parallel. So can we see something quite interesting happening here? There's also, in this direction here's two lines that are also parallel. And in fact, here's another two lines that are also parallel. And here's another two lines that are also parallel.
Just to answer two things in chat quickly. Zoe is talking about adding 1 point around the outside of the complex plane. If you like complex numbers, then there are some situations where adding 1 point around the outside. The thing I've tried to say with, oh no, my two lines that already intersect 1 point show that that's not quite what we're doing today.
It doesn't quite do what we wanted to do that.
If you just have 1 point bit for the horizon,
This bit wouldn't be true.
And the top comment in chat at the moment is, are you talking about when mathematicians remove the parallel postulate? The parallel postulate is the idea that parallel lines don't intersect. So yeah, we're absolutely trying to remove
We're
that.
past that already.
We're trying to remove it to see what would happen if any parallel lines intersect.
All parallel lines tend towards the same point on the horizon.
Well, is that...
Every parallel line converges
right?
at one point. So,
Good claims.
I think I know what these people are getting at. In that, I think the missing piece is all parallel lines with the same gradient tend towards
okay.
one
so
point.
this pair on the left, this pair on the left are going off over there.
Gradient, -1.
Sorry, I can't see what you're pointing at when you're moving the camera.
Yeah. Oh yeah, I'm
Sorry.
moving too much.
This
pair here,
yeah.
perhaps we could say has gradient -1. And then perhaps this pair here could have gradient 0. And they intersect at different points.
Sets of parallel lines
there you
seem
go.
to intersect
Heroes
at
on
a
it.
different point than other sets of parallel lines. That seems nice, I think. So we've got
So
the pair on the left going that way and the pair on the right going that way, and well, we want those intersection points to be different, but somehow each of them, if we looked behind us, each of them associated with the matching other way round.
Matching one at the other end. So we have lots of things that we need to happen. It seems almost like it's not worth the effort. Like, why are we bothering with all this? Why are we going to think about this? Well, I'm going to plot something. I hope, at least. There we are. I'm going to plot something. This here is a parabola. I think you guys would agree that this is a parabola. So, and we're looking at it sort of side on. We've got 0, 0 here. And I'm swapping the x and the y axis around because I don't really care about which way they are. Yeah, you got 1, 1, 2, 4. Continuing on, we've got like 3, 9 there. It's definitely a parabola. There's no trickery going on here. This is a parabola for sure. Yeah, if you say the point of the horizon is exactly the same as the point opposite to it, then it would work. Yeah. I mean, this is sort of what we're getting at, is we want to make a world, almost a mathematical world, in which that is true, and some other things are true, and then we would get a world in which this is also true.
Which might be nice.
And I'm interested in, why are we interested in this? Let's look at this world in which we think that this might be true, and plot a classic shape, so a parabola. So, how do you guys think this will look if I keep to push this parabola off, away? Okay, we've got a guess already. Then eventually they become parallel.
So you're going to show us. You're going to show us. It's also a really big parabola. Give it a second. Give it a second for chat. But I guess I've never asked the question right. Like all parabolas that I've seen before, I'm looking straight at them, and they're quite small. We're about to see an enormous parabola, the kind of one true parabola with all of its shape. But we're looking at it. We're looking at it in a kind of projective geometry world. Which is the one you get, apparently the one you get for free in Unreal Engine 5. That's a bit weird to think about, that projective geometry is kind of inherent in how
lots of
this
guesses that the branches will end up being parallel, and one guess that they're going to tend to the same point.
A second anonymous person.
So we've got lots of people who think, okay, we've got a few people. Let's draw some of these. We've got some people think it might look like this. And then eventually they're sort of going parallel next to each other. This is a horrible looking parabola. And then there's some other people who think that they're going to go out, and then at some point they're going to end up sort of crossing over here. And anonymous said they tend to be parallel but are never parallel. Okay, we've got lots of good things.
That's true about parabola,
should we find
right?
out?
The gradient. I get that, because the gradient goes up, so they're becoming. The kind of tangents to your parabola are becoming more and more
they can't
parallel.
intersect at infinity, because when they're at infinity they're only parallel, so they need another infinity to intersect. I don't see. If only we had some kind of brilliant model where we could figure out exactly what happened at infinity, right? Okay. Some people don't think they'll ever cross. Let's find out what happens. I'm gonna push it off. Ignition.
Go.
Oh, let's see. Okay. Something has happened.
Take your screenshots now. It's the world's biggest parabola.
This parabola is infinitely big, actually. Well, I'm lying, but as far as we're concerned from here,
parabola as far as the eye can see.
Yeah. Unreal Engine 5 would not handle a genuinely infinite parabola.
Good enough. Has chat got any observations? What does chat think about this?
That looks, ooh, that looks suspiciously
Maya says
circular.
if they tend to be in parallel, then it's a bit like parallel lines, and they should
They should
meet,
also
and that's
meet
turned
and
out to be
cross.
the correct intuition.
Whoa, is that an ellipse? That is a good question. Is it an ellipse? So we want to make a model of what's going on here, I think, because we want to know, big question, is that an ellipse? Is it? I want to know if that's an ellipse or not, because it sure looks like it. Look at that. That really looks like an ellipse, doesn't it? It looks like it goes like this, ooh, all the way around.
I love the way your
My
character your
goodness.
character in Unreal Engine seems to have a small collection of boxes and a laser pointer, and that's what
That's all I need. That's all I need.
video game coming soon where you point the laser at the boxes.
Yes.
They
From
do
our
look like they're
viewpoint,
bending to each other. And
the
can we address
circle.
this thing that I saw it go past in chat? The parabola is a 1-to-1 function. I guess it's a 2-to-1 function. Where if you draw it on regular graph paper, it never curves back in again, right? Because it never has that kind of multi-valued bit. So it looks really weird that I think I can point with not just my cursor, but this bit looks like it's on top of that bit, which wouldn't happen for a normal, when you just draw a parabola on normal paper. But kind of this bit represents, I suppose, the value of x, where if I read down to the x-axis, I have to read down like this along the grid line.
Yeah. Now that's
Off
the
the screen.
secret, because over here, so I'm doing a bit of trickery. I've made the line really thick as it goes on, because otherwise you can't really see it, so it looks a bit rubbish. But say it intersected here, you'd have to draw all the way down here, and that x value is ages and ages and ages and ages away, like over here somewhere. Over here, you're looking at an x value like there. That's ages away. If I move this way, you can see,
Oh, crikey.
right, that the x value for this point here, let's track it. Oh, that does look like that does look like an issue. It looks like it's crossing over with this one, right? But I can assure you that it definitely is not. Just looks like that from our perspective.
Okay,
That's the fun about having this visualization on Unreal Engine. You can do things like this.
You can go and look at it from somewhere else, I guess.
Yeah.
So we've now got on screen what a parabola looks like if you draw it on the floor and stand back and have a look at it. And chat's onto something by suggesting that it looks round, maybe a circle, maybe an ellipse, maybe. Oh gosh, sometimes I find it helpful to look at it kind of sideways to judge its. Does it look circular or more ellipsy?
It's not. It's
Because I'm so biased
elliptical, I
by
think, yeah.
human vision interpreting this as the real world and trying to work out
It's
what
quite
shape it's
circly.
got. There's a bit of an optical
Okay.
illusion thing going on, maybe.
I think we should try and make a model of what's going on here. We're
Good
looking
idea.
at things through a camera. We have camera vision going on right now. I want to know about the maths behind camera vision. So let's get started on that, I think. I want to know what's going on, so I will model. That should be a quote somewhere. I'm sure that's a quote somewhere. So let's go over here and let's make a world. And I'm gonna make, for now, at the beginning, I shall be aware that I am in a 3D world. So there is 3 axes, and there's some grid lines and such things. Let me be in black. And people stand in this world and do things. But I'm going to look at a 2-dimensional cross section right now of this world. So we had at one point Z axis, Y axis, X axis, 3 dimensions. But I am going to look at, just for now, the Z axis and the X axis. That's what I'm interested in. And we're doing cameras. So what I'm going to do is I'm going to place a 360-degree camera at the origin. I'm going to put the origin at the top of the screen. You'll see why in a second. Here's the origin. Here's the x-axis. Z-axis is up and down here, right? Maybe I'll just do. And I'm going to put a 3D camera up here. Just like those ones that you have on your GoPro on the end of the GoPro. And the reason I'm doing that is because I sort of want to know about what things look like from all the directions that I could look in. And so I'd probably want to put a camera that can see in all directions for now. And oh dear, I've got an alarm set. Let me get rid of that.
Oh no, is it an alarm reminding you to?
I think so.
So you
Okay.
call this a 360 camera because it can see in every direction.
Yeah,
And
I'm
guess
just gonna have it
the
seen
maths
every
of how the
direction.
camera works is kind of interesting, and turns out to be the maths of how projective geometry works as well. Sorry,
Well,
covering for you while
this
you do your
place where we are in the
live.
camera, we're seeing through a camera right now, and it certainly looks like this special postulate that we made up is true. So it looks like good things are happening. So I'm going to use the camera as my sort of inspiration for what's going on. Anyway, so this is z equals 0, and at z equals -1. Now I'll do a bit of forewarning. Generally speaking, people do this construction up top. So they put the plane here. I'm about to put the floor in. I'm going to put it at z equals -1 as a floor. But generally, people put it up top at z equals 1 as a ceiling, just because they don't like to have negative numbers involved in all of the stuff that I'm about to do. But I want it to look like my floor here, so I'm going to put it on the bottom. It doesn't actually matter. We'll get to that in a second. So let's pick a point on this floor. Let's see, A here, which is at 1 on the x-axis and -1. So we've got 1, 0 on the y, because I'm just looking at cross-section y equals 0, and -1 on z. So that's A. Brilliant. What does that look like from my camera? Not really anything very interesting, right? It's just, imagine that we had camera view here. Let's see, a little box. This is camera view. And we see A here. Interesting, right?
When you come on the live stream, we check your art skills to see if you might be, making me
Yeah.
look bad. But you've passed this.
Not
Okay,
much going
so you've
on.
got your camera. Is it your camera's looking? Which way is the camera looking? I guess it's looking every direction.
Yeah, we're not worried about where the camera's looking,
Of
really.
course, it's looking every direction.
What I shall do is to represent how the light from A gets to my camera. I'm gonna have this laser pointer. I love laser pointers. Come out from camera to A, and this is the path that light would take as it went from this point A to my camera. So if we all know cameras work because light comes to the camera and then it detects it in a sensor or whatever. This is how it works. Yeah, right. This ray of light here, I'm going to say that imagine this plane here wasn't actually at z equals -1, but instead I had it at z equals, what should I go for? Z equals 1/2, maybe. So I'm going to redraw it in here, z equals 1/2. There is a slight interesting thing in that this point B, which is now at 1/2, 0, -1/2, that would look the same, surely, according to my camera, as the point A, because the direction that the light comes in to the camera is the same for both point A and point B. So according to my camera, what I see, okay, I can't move like that. What I see over here is A, and then on top of it, we can't really see at all, it's just B as well. B is also there. They're both in the middle.
So you're kind of losing information, right? You're in a 3D world, but your camera view, or I suppose what you were showing us on the screen, this live stream, it is 2-dimensional. So we're losing information about the 3D world. The parabola is on the floor in 3D world, but we're projecting it, I suppose, onto a 2D plane by thinking about the lines or the directions that you would look in to look at each part of the parabola. That sounds a bit mad, but I think it is.
So the big issue
projection
is that B. Can I distinguish between B and A? Actually, imagine that instead of B, there was a tiny, tiny, tiny hole in this plane. Oh dear, that's not making a tiny, tiny hole. How do I make a hole? Maybe like this. Imagine instead of B, there was a tiny hole here, and A was there. Would I be able to tell the difference between that situation and the situation in which B was there and covered up A? I don't think I would. Aha! Someone's already gotten to what I was going to say. Yeah. According to our camera, B, so this point on the plane, is essentially the same point as A. We can't tell the difference between B and A from here. Nor can we tell the difference between B, A, and some other point. Let me try and make this a different color. Another point C here, or another point, maybe D down here. If they're all on this line, then they all look the same to the camera. So maybe a different line, a different point here. This one looks different from C, B, A, and D. We can agree. Someone's just written no in chat, which is an interesting response.
Maybe they're responding to the idea of 4D eyes, which sound like too much. Oh, they're answering your question, I think, which is would A and B look different? That's chat lag.
Yes. No, A and B don't look different. C and D, they all look the same. C,
Okay.
D, A, B. We can't tell which one is that actually there. But E, this one is definitely, according to our camera, this is a different point altogether. E would be like this down here, right?
Depends which
If I
way
was
up
looking
is.
at it down here.
Yeah, okay.
Yeah. Yeah, I'm making an arbitrary decision there.
Sure.
So E is a new point. We can tell the difference between E and these ones because it doesn't lie on the same line from the origin. And here's where I'm going to bring in. Someone just said, if points are on the same line passing through the origin, then they are essentially the same point. Yes, according to the camera, points on the same line that passes through the origin. And what I'm going to do is I'm going to call it a vector line, which I think we're all familiar. If we've done GCSE maths, then we're all familiar with if I have some vector A and I multiply it by 2, then I have a vector that's double as long and it's in the same direction. Say I multiplied it by -2, then I would have a vector same length, but it's going the wrong direction, like this way. And I can sort of multiply this A by whatever I want, maybe a half, and a half A looks like this. It's the same direction, but it's half as long. This is a classic sort of GCSE maths thing. We have line of invariant points. Okay, that's some linear algebra. So we do have a line of points, but not necessarily invariant ones because there's no transformation. I mean you can do them, but we're not going to worry about that today. So this is half A, that's normal A. We've got many different things. I'm going to call a vector line a line of all the points that I can reach going along one vector. So if this was the vector, let's just call it V. This vector here is a vector V. All the points that I could reach with a multiple of that vector lie on the vector line KV. So this is a line. Oof. Oh, that's rubbish.
I love
Line.
that chat.
Ooh, that goes all the
Sorry,
way
I'm
through.
jumping in. I love that chat's mentioned modular arithmetic, which
That's
we had a few
brilliant,
weeks
yes.
ago, right? And I'm always trying to get people to think about modular arithmetic as just one sort of removing information or quotienting, where in modular arithmetic you ignore the multiples of p for some number.
An equivalence relation, absolutely.
Yeah.
That is.
Here we're considering. I guess what we've discovered is if you look in different directions, you see different stuff. But if stuff is behind the other thing, then that's the same direction.
Tell the difference.
Something I like about this model is while I'm interrupting, is that the pointer infinity fits in really nicely into this model of different directions for different points. Could you draw me a red laser pointer for what it would look like to point your laser at infinity?
Let me just clean up the diagram a bit. And
Okay, so we've got points. I like A, B, and C being some normal example of what pointing a laser.
I can't get rid of anymore. Yes, we've got some stuff here.
But the point in infinity fits in really nicely. Maybe you can check and see where we're pointing.
Yeah, I want to do a bit of a sort of argument here. So this point
good.
is a point on the plane as well. Let me draw the lines in fully. This point is also a point on the plane, right? And that vector would be, I don't know, let's imagine that is the vector 2, 0, minus 0.5 there. And all of the other points that I can reach by multiplying that by some constant k are also on that vector line, indistinguishable, such. Let's try another one. So let's try, oh dear, one like this. Eventually, if you agree with me, eventually this will reach some other point on the plane. This one will reach some other point on the plane eventually. This one will reach one other point on the plane eventually. We're really, really far away, right? This is a really far away point on the plane that it's going to reach. So if I say that a projective point, so this, what I'm going to call the points according to the camera, so things the camera can see, I'm going to call them projective points. So points in the set of this set. This is what I'm calling it. Projective points. Projective points, if I want to say that they are vector lines through the origin. Because the only thing that's important to my camera is what vector line on the origin they're from. And according to the camera, if they're on the right vector line from the origin, then they are the same point. So I want to say projective points are vector lines through the origin. There is a vector line through the origin that does not actually appear on our plane. And that is this vector line here. As the one that James wanted me to draw a long time ago, which I've just gotten around to drawing. Do you want to take over?
Oh, not really. I don't know. I just feel bad that I made you point the laser at infinity. But it fits
laser,
so
yeah.
neatly into the picture here that if you're thinking about points instead of being like one literal point in 3D space, if you're thinking about them as being different vector equations of lines or different directions, then again there's a kind of missing gap. What about a line parallel to the plane that you could just sort of fill in? And I really like it when an innovation kind of fills in a gap. It's reminding me a lot of putting in the square root of -1 as a sort of number that helps you solve an equation that you couldn't otherwise solve. Let's invent an extra thing that kind of satisfies that. Here we're kind of inventing the point at infinity as being, okay, the laser pointing at infinity.
It almost seems to magically have appeared from just thinking about how the camera sees things. We're like, oh, so this camera sees everything on the vector line as the same. So maybe the things the camera can see, this set of stuff camera can see, is the set of vector lines through the origins. And if we look at that, then we find there are things that the camera can see that aren't parts that were on our original plane. And that set of all these lines, of course, we're looking at this 2D cross section right now, but when we take back a look at the 3D, there are loads of lines, right, that could go in all directions that all don't intersect the plane. And every single one of those vector lines, there must be some extra point that we didn't actually have before on the plane. And it's the point that you approach if you get further and further away with our intersection on the plane. So you just imagine that this sort of line here is the plane. If I went really, really far away, like stupidly far away on the plane, and I drew a line back. Let me do it. Let me get stupidly far away and draw a line from there. As I get further and further away, that line gets closer and closer to being the same as these extra ones, these ones where z equals 0. So it seems that these extra points that you've added in, you can approach them on the plane by going really, really, really far away, but they're not actually on the plane. You can only approach them. So according to the plane, there is no point at infinity. It's not a thing. But according to our camera, or our model that we're making right now, they are a thing. And if they're a thing, then they're a thing that we can think about mathematically.
Someone in chat asks, is the camera at infinity? And weirdly,
the camera is at the origin.
The camera's just at the origin and we're looking at infinity.
I've popped at the origin.
But I will give you something at infinity if you like. So something I like a lot about this is once you've decided there are lots of different points at infinity for all the different directions, so that direction, all the different directions that are parallel to the ground, different points at infinity, natural question is there a line that just goes through those points at infinity? And the answer is yeah, I suppose so. You could have a line that just goes around the horizon, which people sometimes call the circle at infinity. A sort of special line that goes all the way round. That works. That's still consistent with our idea that any two lines should intersect at exactly one point, or any two distinct lines. Sorry, because if you have one normal line and the circle at infinity, then yeah, your normal line goes off to infinity where it hits the circle at infinity. Kind of in front of you and behind you, but we agreed those are the same point secretly. So it still works, still consistent.
Yeah.
Also, there isn't space for a second circle at infinity because then they would intersect too many times. So you kind of the restriction of all lines meet at one point is weird.
Because it seems like it's a bit silly to suggest that if I drew again my axes here, and oh dear. And I have my camera and a plane down here, and I found some points A and B. Oh. Et voila. So A here, B here. It seems really silly to suggest that A is this point as well. That's behind it. How could it possibly be that point? That's ridiculous, right? And B is also this point. But let's say that those were actually points on the plane, right? So that this point on the plane B and this point on the plane A is a point on a plane over here, right? The plane would be, et voila, like this. So then A is here and B is here. If I'm trying to look at things on this plane and it was behind me, then the plane is actually, the floor would be above me. And if the floor's above me, then I'm upside down. And if I turn myself back around, you would find that A and B are actually where you would expect them to be. So this sort of strange case where the lines are behind me, when usually I'm just looking at things in front of me on the camera, actually turns out to be the same thing as the case if I was just upside down. So there's no issue with this.
There's a gluing question in chat which I want to take. Are the edges of the plane? So I've been talking about infinity, where the circle at infinity, the front half is kind of glued to the back half. And there's a question about whether that makes it a torus, which is such a good question. Topologically, the answer is perhaps weird. No. You've got the right idea that gluing it together would give you some kind of surface without an edge. That the bit of infinity, you can keep going past it and come back in again in the same sort of direction, walking along that line. But it's not the same as a torus. It turns out to be a different topological surface. There's a model of it where you can identify the sides of a square in a different way. Miles is drawing this now. So that's a torus. If you take a little square and you glue the edges together. Wait, I could do this on a bit of paper. I have paper. You glue the edges together and then you glue the top to the bottom. Our world is slightly different because the direction is all the same. The way you glue together is not those bits glue together and these bits glue together and those bits glue together and coming around here. The way you glue together is that all the opposite points glue together, which kind of puts a weird kind of twist in it.
I feel bad. Everyone's trying to imagine it in their heads. I'm afraid that it's four-dimensional.
No, I mean you can't embed it in 3D.
You can't.
It's more like
embed it in 3 dimensions.
I've loved that we've gone here. It's amazing.
It's close to being a Klein bottle, I think.
If you've seen a Klein bottle, you've seen that kind of self-intersecting shape. There's a way to roll that up, but it involves twisting it through itself in a way that doesn't embed nicely into our universe.
It's a 2-dimensional Mobius strip. I think everyone's saying that it's a Klein bottle. I don't think they're actually the same thing, but they're very close to being the same thing. Yeah, if I correct me if I'm wrong, this is a bit outside of my subject knowledge.
Klein bottle would be if you flipped one of the arrows.
Yeah, this one's both of them. Yeah,
it's turning into a topology quiz.
This is getting.
There's several things you can do, and they're not all the same. Yeah. It's brilliant.
So we have our sort of 2D stuff, and we're quite happy with it. Let's now move back into 3 dimensions and get a proper look at what's going on here. And this is where, James, I might ask you to aid me with the drawing, because this is where it gets
right. My turn to come in tomorrow.
Yeah, I'm going to try and draw.
No.
It's kind of the wrong way up, isn't it?
I can't come in tomorrow. It's.
Oh.
I can't come in.
Okay.
It's too much for my computer.
I've done a good one, though. I've done a good one, so I'm quite happy. We've got the origin. Okay, I'm going to cheat. I'm going to put the origin up here because that's how I've drawn it. The origin is here with our camera on. You know, we have what we were doing before, all the stuff happening. There's maybe points A and B that we were looking at ages ago, and all these lines, right? And we have all these lines where z equals 0, which seem to correspond to some points that aren't on the plane at all, but like sort of only exist according to the camera. Someone asked ages ago where those points were. So if I look down here, I'm seeing the plane, seeing the plane, seeing the plane, seeing the plane, seeing the plane. That is like my camera, you know, seeing the plane, seeing the plane, seeing the plane, seeing the plane, on and on and on. And as I look really, really, really far away, I'm still seeing the plane, but I'm seeing so far away from me. Like this must be like X in the millions or something like this. And then as I just look at the horizon, my camera is perfectly pointed straight ahead. That horizon line is where the points at infinity are. Because if I pointed myself straight ahead, then my sort of like direction of vision is straight along z equals 0. There's a big plane where z equals 0, which is like sort of this, and then coming around here as well. That's a pretty good drawing. But yeah, so that's where the points at infinity are according to our camera. They're right at the edge of where we can't see the plane anymore. Straight ahead of me. So are we doing torch thing now, James?
Yeah.
I think we're doing torch thing.
I've got this way of imagining where you imagine, I guess more like the laser pointer of light shining out from the origin. That's like if I know the camera takes in light, but bear with me. If you replace the camera with a torch, then you can imagine points where, as you're shining light out from your torch, they're going to hit the plane at some point, and you can find out what. And that relates quite neatly to what it will look like.
We had laser pointer before, so
yeah,
maybe a torch isn't so shocking to imagine. That's a rubbish yellow. A torch wouldn't be so shocking to imagine on our floor, right? It's just, I mean, a torch is essentially just lots of laser pointers if you think about it. So maybe
lots of laser pointers arranged in, crucially, I suppose, a circle kind of configuration. I guess torches, instead of having a 360 degree of firing lasers in every direction, like your 360-degree camera was trying to look at light in all directions, that's too much for me. If I imagine a torch with some sort of aperture, then I only get light in, I suppose that's a cone. I suppose, I haven't really thought about it. If the end of your torch is circular, then as the light comes out, the kind of circle gets larger and you get this kind of cone shape, which you've drawn on the board beautifully.
Yes. So. And we're adding, because our lines are vector lines and they can go the opposite way, then we will have the sort of rest. We've got a double-sided torch, like a lighthouse.
Because you want directions to count. I get it. You want directions to count as the same if they're just a multiple of each other, including negative numbers.
What if I was upside down and the plane was on top of me? Then I would still want things to be there. So
sure. I'm not aware of any.
This same argument from earlier. We need just as we need the lines to extend up here to account for when the plane might be upside down. We also need a torch to extend up here to account for this as well. So we've got sort of a Darth Maul torch, essentially, and we're shining at the floor, and this is definitely where it intersects the plane here. It's definitely a circle as far as I'm concerned, or some kind of elliptical shape.
Yeah, it's a circle if you point it straight down. That's kind of a nice.
Yeah, I'm pointing it straight down. We've got a circle going
on. But you can get different shapes on the plane if you point the torch in different directions. And whether or not we do the maths, I think that's something to try at home. If you've got a torch or your phone torch or something, hold it quite close to the floor, point at the floor, and try pointing it in different directions. So if you get a nice, neat circle of light, what happens when you point it in different directions? And in some
let's see. Let's point it a bit ahead of ourselves. So maybe we're pointing it like here, oh, that's pretty good. There we are. So now I'm pointing it sort of over here, and I've got behind it all the other bits going on. And the absolute the top of my torch currently is like this beam right here, right? This laser going from here to here, and the upside down thing. Okay, we can do the upside down thing again. So
I think for now, let's just say that the direction we're being we're counting twice as far away and 3 times as far away as doesn't matter. The light's going to get there at some point.
Yes.
And we're also treating negative numbers as well, so that once you've decided what direction some light is going in, we're counting everything forwards and backwards. Your intuition is maybe that if you point it straight down, you get a circle. If you put it ahead, then you get a kind of squished or stretched circle. And
yeah,
really
you get it's ellipse, isn't it? And then let's keep pointing this. If there's stuff above you, then if there's stuff above me, then the sky there would be another plane. Well, there is someone else made an app where there is another plane above you, and I could have used that one, but I did like the sky, and also you can move around in that one or do anything fun.
I think we should focus on having one bit of ground.
We're just having one bit of ground right now. Well, the case where the plane is above you is sort of a separate case. So this is if I said my plane was not at z equals -1, but instead I said my plane was at z equals 1. then I would have a different case. It's a different plane that I'm looking at with my camera. But what I'm saying is that if I was looking at a plane where z equals 1 and I saw 2 points A and B, I would not be able to distinguish between looking at a plane where z equals 1 and seeing that, or upside down, looking at a plane where z equals -1 and seeing the same thing. Those two cases are indistinguishable according to this 360-degree camera. I can't tell the difference.
Cool. So people in chat are getting ahead of us because there's a bit of maths that helps you do. Well, there's just some words for this from. The words are conic sections, but it's kind of not really important what they are. If you know the equation of a cone and you know the equation of a plane, then you can solve those simultaneous equations to work out what shape the intersection is. I guess that's what we're doing. We've got a cone of light and we're intersecting the flat plane of the ground, and there's some not terribly difficult maths for what happens as a result. I guess the hard bit is writing down the equation of a cone that's pointing in some direction. We want to be able to move our torch around and think about pointing the cone in different directions.
Yes, just to make really clear what's going on here, my torch beam isn't changing size. I'm not changing the size of my torch beam. If I was to draw like a sort of a sphere in here, then the size of the torch beam's intersection here is the same as when I push it more up and it's like over here. But what I'm doing is as I move it out like this, my torch, then the intersection with the plane gets bigger. Things change with the intersection with the plane. My torch beam isn't changing, but how it intersects the plane is.
Yeah, like
So,
if you shine your torch at a tree that's really far away, you might be able to light up the whole tree. But if you shine it at a tree that's really nearby, then it's the sort of thing where you say it in words and it sounds really daft, but yeah.
yeah. Anyway, so what I want to do is, some of you who know conic sections might know how to obtain a parabola from doing conic sections. I'm just going to go for this parabola in here has one single it appears to have one single intersection with a point at infinity way off, right? So if I have a circle torch beam that's like here, and I move it out and out and out and out until it just barely touches the horizon, there's one single point at infinity on my, like, sort of in my torch beam's reach. In this it's not a shadow, it's the opposite of a shadow, but in the shadow that my torch casts on the ground, there's one single point at infinity right at the tip. And that is what I shall do. I shall now, hang on, let me actually delete the other torch beam because that's going to get in the way. I shall now shine it. This is where I wish I made a second software that could do this bit for me, because hard. If I shine it like so that just the bare top of it is to the torch beam, that should probably be like that. But just the tip of it is z equals 0 on this very tip up here. It might be hard to see.
So the top of the cone is parallel with the plane.
Yeah, the top of the cone is parallel with the plane, just the top. And what gets cast on the ground, if I draw it in, let's see how good my drawing's been. So that's sort of the ground there, that's sort of the ground there, that's sort of the ground there. You might believe me if I told you that this shape here is a parabola on the cone. And if you know conic sections, then you can guarantee that it is the case, because with conic sections you have this cone like this, and you pop a plane through it such that this gradient of the plane is the same as the gradient of this side here. And you might know, if you do that, then you get a parabola here. That's on the further maths spec for A level. So some people who do further maths will know this already. So these are the conditions for a conic section for the intersection being a parabola. Et voila.
My lazy version of this is it's clearly something quadratic, because cone has got x squared and y squared in it. It's clearly something quadratic, and it is going off to infinity. So could be a hyperbola, but it's only got one bit, so probably not that. Probably not an ellipse. It's the other sort of quadratic thing, where I'm falling back on my lazy knowledge that there's not that many sorts of answer for a conic section problem. I thought I learned about conic sections at university, so I'm a bit surprised that some people get to learn about them at school. If anybody in chat is learning about conic sections in school, then we've accidentally done some revision. Yeah, top comment is not on my further
Not
maths
on
spec.
my, oh well.
What about, so
Okay.
the other one we mentioned there was hyperbola.
Oh, so
It's a
I've
different
got
sort of
just
conic section, right? Where
I've got just
you...
one tiny bit here,
Oh yeah, okay.
touching z equals 0 of
Mhm.
my torch. What if I was really, really, really silly and I shine my torch like? Ooh, now the question is, do I draw this on that? Yeah, let's do it. What if I shine my torch? Let's do a different color, like this, so that there's two different intersections with the plane z equals 0. Now I should have two crossings with points at infinity, two different points at infinity. And because we have that, the line up here corresponds to also points down here, what's going to happen is, firstly on this side, you might believe me, you might not, but we're going to get a hyperbola sort of torch beam. And if you've ever shined a torch beam sort of straight ahead, then you might have seen something that sort of looks like a hyperbola on the floor. But the question with the hyperbola is there's stuff on the other side of me with a hyperbola. Let's actually tell you what. I thought ahead here, and I have a hyperbola
Aha. Is the green thing is from
in the
hyperbola?
software.
Ah, there you go. There's a green hyperbola.
So imagine I had a torch in my hand right now, and I shined it straight ahead here. So
Stand still a second.
Torch beam here. Oh yeah.
Stand still a second. Okay, hyperbola. Stand still. Your engine is very exciting. It lets you move around, but I want to look at. Okay, so we're imagining you're shining a torch kind of ahead of you, and the claim is from some sort of algebra that we're avoiding doing, but some conic section algebra, that the shape you get on the ground would look like this. I guess that's supposed to look like.
Hang on. Let me make it a bit. There we are.
Ah, okay.
Now it looks a bit more like how it should look. That's just because I was not on the origin. If I'm on the origin and I look up, then it should be quite good looking. Yeah, there we are. Yeah. So this shape is the sort of shape that you'd see if you shine a torch straight ahead of you. I think people who've done that before will appreciate that. And according to like our stuff, there should be a torch beam up here, right? But because we're dealing with this projected space where the points on one side of me, so these points here, are essentially the same thing as the points on the other side of me here. Points at z equals 0 are the same in front of me and directly behind me. All this stuff is true. Then I can actually take the points that should be up here and pop them behind me. If you ever plot...
There was a turnaround there. Do you want to turn around and show us both halves? Yeah, it was a little bit fast.
Yeah.
We're too fast for me.
So you can imagine, for instance, that I shine this torch beam and in the sky there was a massive reflective dome that reflected the rest of the torch beam behind me back onto the ground. This is what we would see genuinely in real life if we did that. Quite a powerful torch would be necessary, but
Kizzy and chat's talking about reflections, and there's something about if you follow the hyperbola off that branch to the right, then you come back. You put the lines in. Great. You come back at the kind of equivalent point behind you at the kind of point in infinity on the other side. So there's kind of a reflection thing going on.
Come back, right? These lines were over here, and they come back, right? You would come back over. You would go over here, and you would come back this way here. And something quite fun. I don't know if we've got time. We've got 1 minute. Okay.
We've got a minute.
But there is this place that we've made that we can properly do some proper maths and model it with actual coordinates and stuff instead of just drawing things on a whiteboard. Is an example of something called a non-orientable manifold. And this is topology again. But what that means is if I had a man on the inside of this ellipse here, like that, and I sent him around, and he went off to infinity, and he walked all the way to infinity and back, then when he came around this side, he would be flipped over. So over here, he was facing this direction, facing inside, voila, this way. And when he came back, he would be flipped over and facing this way, and he would come back like this, and still be on the inside. And what that means is I can send this man in circles around here, and he would always be inside of this sort of ellipse that's been split in half. There is an ellipse to be seen here that's split in half, one on one side, one on the other.
Cool. And it comes back to this. This idea about identifying the opposite Points at infinity
Yeah,
as the
identifying
same as the
opposite points
same
are the
as
same
the
thing.
same point, the ones that are directly opposite. Okay, thanks, Miles. There's one thing that I wanted to draw quickly. I don't have the pen, so I'm going to get you to draw it.
Okay.
And I'm going to get people to draw at home. We're going to overrun by just 3 minutes. Because I have another example of a space where any 2 points, there's a line through them, and any 2 lines meet at one point. We're going to draw it together. I would like Pac-Man. Again, no,
So,
not
and someone
Pac-Man,
anonymous
not Pac-Man.
mentioned games where you go over the edge.
Ah, okay, there are ones like that. Okay, interesting
That's
topology.
like Pac-Man.
We should do a
Anyway,
topology episode at
right.
some point. Can you draw this for me? I'd like an equilateral triangle, please,
Do my best.
with points with a point at each of the corners. And then I'd like a point at the middle of each of the sides. I'd like 1 point in the middle. Those are my 7 points. I've only got 7 points in my space.
You want lines?
I'd like some lines, but I need to draw a line between any 2 points, so that for any 2 points you can connect them with a line. So yeah, that one. But I'd like you to keep going through to the keep going through. And one more line. The 3 midpoints. Please, could you draw a circle inside?
Circle.
People normally do a
Okay, hang on a
circle.
minute.
People normally do, because it's one curved line, if you like.
Like this.
Yeah, like this. A little bit like the Deathly Hallows symbol from Harry Potter, but
Yeah, that was about to say.
rotationally symmetric. This is an example of a space where, you're going to have another go at the circle.
Yeah. Oh, it's gone worse. It will do.
It'll do. This is an example of a space where between any 2 points, there's a line, and any 2 lines meet at exactly 1 point. It's got the property that we've been investigating. Its only distinguishing feature is that instead of infinitely many points, it's got 7. And I think that's cute. So it also does the thing that we've been investigating, which is kind of a different postulate, I suppose. It breaks a lot of the normal things about geometry, because who said you had infinitely many points? Why not just 7? That's called the Fano plane, Fano. I'm a big fan of
we've got this
the Fano plane.
massively complicated camera trickery business like this, and then we've got this.
This is kind of the simplest example of a space where any 2 points have a line through them and any 2 lines meet at a point.
This is still true. It doesn't matter whether there's no such thing as cheating if it's right.
Maybe they're not happy about my curved line,
Yeah,
but I suppose the curved line shows that you can't embed this in Euclidean geometry using straight lines. I have to draw it in a weird way like this. Right, thank you, Miles, for drawing for me on a week when I have no access to drawing. And thanks for showing us projective geometry.
Yes.
We've overrun very slightly, but it's
We
been
have a
good.
little bit. I could make this app available in further reading.
We'll see if that happens. The further reading is posted. Thank you for the reminder. The further reading is posted on the Maths Club website each week. Oh, you have credits.
Yeah, just for the outro. I thought I need to put it up there.
Oh, brill. The further reading is posted there, where I will put some maths about conic sections in case anybody wants to learn more about that, because it's not on their FM spec. And we will put some other stuff about topology. We're probably going to have to do a full topology episode at some point because it's come up a couple of times. That was your episode on projective geometry. If
This is called projective geometry. We made a space called RP2 today.
Yeah, RP2, which is almost just as important as Mobius strip, Klein bottle, sphere, RP2. They're kind of there's a small set of these examples of interesting geometries that you define in a similar way. Right, good. You're giving them facts about RP2.
There we are.
Good.
Some facts.
Thanks for coming on the stream. We will be back in 167 hours for another episode of the Oxford Online Maths Club. We'll catch you around. Take care, everyone. Bye.